All right. So I've got 405, so I'm going to get started. This is COMP2804, Discrete Structures 2, and I'm the instructor, Daryl Hill. So we're here on the 31st. We're going to take recursion today, so you guys have handed in assignment 1. Assignment 2 is ready. I'm just trying to get some TAs to proofread it to make sure I haven't said anything really dumb. Probably I have. But so that should be released either tomorrow or Thursday. But of course, Thursday is the test. So do show up with a pencil and a calculator. So those are permitted. It's going to be multiple choice. Some of it will be very, yeah. Right. So back when we had See You Learn, I could make the due time 11:59, but I could secretly make the server open for another hour or two, right? Just for people who submit 10 minutes later, or whatever. With Brightspace, I can't do it secretly, so I just make it 8 a.m. But that is a hard deadline, so if you miss that, it's 0, right? So just upload something before then. It's going to say late. I don't care. You won't lose marks. You do have until 8 a.m. Yeah. Okay. Yeah. Yes, you should definitely go to your section to take the test. You cannot go to the other section because these rooms are going to be full. So yeah. All right. Other, yeah. 17. Yeah. Some people are done in 20 minutes, and others, I don't know if those are good or bad, but I know some people walk out after 20 minutes. Other questions? Yeah. Yeah, it's just multiple choice. These are marked by Scantron. I mean, there's 600 students. It's between the two sections, it's a lot. So yeah, that's unfortunate, but so you can, because they're multiple choice, you can give yourself some advantages, right? You can rule out questions. So yeah, use every strategy at your disposal. I'm actually kind of bad at multiple choice questions. I don't like them. So I usually score a little lower than I would normally, but I mean, it's the best we can do with classrooms this size. Yeah. All right. Other questions? Yeah. Yes. Yeah. So it's going to be pretty jammed. As difficult, there'll be exactly the same difficulty as the practice midterms, the old midterms. Yes, Scantrons work with mechanical pencils. What can be submitted until 8 a.m. is the assignment. So you may have noticed that the Brightspace server is open till 8 a.m. for the assignment. I wish I could hide that information, but I can't. So the soft deadline is midnight. The hard deadline is 8 a.m. So if you're going to try and submit something up to the deadline, I recommend submitting something before that, something earlier, so you at least get marks if you miss it. And the other are calculators. Yes, you can bring calculators to the test. That's it. Pencil, calculator, it should be good. All right, other questions? Yeah. Should be non-graphing. I'm not going to go around and check everybody's. I don't know what kind of. I don't know. I don't even think that would give you an advantage, but yeah. Other questions? Yeah. Sure, but the test itself is single-sided so that you have the back to work on. But yeah, if you need, I'll see if I can bring some extra paper in case somebody needs it. Yeah. Yeah. What's that? Yes, that's it. It's just the test. Nope, there's no lecture. It's just the test. 80 minutes. Yeah. Correct. Last topic is Pascal's triangle. Everything after Pascal's triangle will be on assignment. two, pigeonhole principle and recursion. Recursion is kind of short. So it's 4 lectures total will be on assignment 2. And then we'll start probability. And then everything, pigeonhole principle up to the end of probability will be test 2. Right. Sorry, other questions or? Okay. All right, so yeah, we talked about pigeonhole principle last class. This class we're going to talk about, oh, there is one here. Bring your coats and bags into the room. Yeah, you can. I mean, we're gonna be wandering around, me and a couple of TAs, making sure you know everything's above board. But other than that, I'm not, implementing a ridiculous amount of security. So yeah, you can have your bags and coats. Just don't be reaching into your bags or pockets. All right. Other questions? Okay. So recursion. So you've probably encountered recursion when you're programming. We can define it mathematically in a number of ways, but the base definition is I'm going to define an object in terms of itself. So there's an object can be a function, a sequence, an algorithm, a set. I think that'll come back. Or not. Okay, good. Yeah, so it can be a function. We quite often express them as functions. Functions are sort of versatile, but it can be a sequence, right? I can have a sequence of numbers that are defined recursively. That's not a problem. Recursive algorithms, of course, that's sort of our bread and butter as computer scientists. Recursive set definitions, things like that. But for starters, we will talk about functions. So this means a function f from the set of integers to the set of integers, right? So I put an integer in as a parameter and I get an integer back as an answer. So for example, f of 0, in this case, I define to be equal to 5. Now, this is not recursive. This is what we call the base case. Okay, so every recursion, whatever it happens to be, you need a base case. Otherwise, it goes on to infinity. So I need some sort of stopping point for my recursion. In this case, we'll say f of 0. And then I can recursively define a function f of n is equal to f of n minus 1 plus 2n minus 1. So this is just sort of some arbitrary expression. But the key is that I have the function itself on both sides of the equality. Okay, so, and the other key is that, of course, these have to be different values. Typically, the smaller value goes on the right-hand side and the larger one goes on the left. I imagine you could define it in the other direction if you wanted to. But, so given this definition and my base case, now I can start figuring out what these functions resolve to. So f of 1, so f of n minus 1 is f of 0, and then plus 2 times n, which is 1. So this is 2 times 1 minus 1. I know f of 0 is equal to 5. So this is 5 plus 2 minus 1, and that's equal to 6. Okay. So if I just have the recursive definition alone, I can't resolve this to a value. But given the recursive definition and my base case, then all of a sudden it becomes defined. Likewise, f of 2, I'm going to, well, f of n minus 1 in this case, n is equal to 2, so n minus 1 is equal to 1. So I'm going to substitute the value 6 in for f of 1. Plus 2n is plus 2 times 2, and then minus 1 minus 1. Again, I'm substituting 6 in for f of 1. So I get 6 plus 4 minus 1 is 9. Okay, so, and I can keep going like this, and I can define f of 3. Well, it's equal to f of 2, which is 9, plus 2 times n, which is 3, minus 1. So that is equal to what, 14? 13. No, 14, yes. Yes. Right. Incidentally, yeah, thank you for the students who spotted the errors in the assignment solutions. Yeah. I've tried to be careful, but I do sort of have a tendency to transpose numbers and do dumb things like that. But yeah, so 14. Okay. So the keys to my recursion is 1, I need a base case. 2, I need to define a function in terms of itself and maybe some extra stuff. And the argument on the right-hand side should be smaller than the argument on the left. Or more generally, it should be different, right? It should be something different so that as we go through the cases, we eventually get down to a base case. Okay, so we have a recursive definition, which is sort of useful, but sometimes we want to put this definition in what's called a closed form. And all that means is that I'm going to express it as usually a function of n, but not a recursive one. Not a recursive and also not iterative, right? So by that I mean, we've seen, of course, things like this, whatever, 2 to the k, right? So that's not a closed form, that's an iterative form. We want simply an expression in terms of n. So how do we go from a recursive function to a closed form? Well, we're going to, we're going to unfold it a bunch. We're going to find successive values for this function. We're going to find a pattern, hopefully. We're going to guess at a solution and verify by induction. So number 2 is probably the trickiest part. Sometimes, hopefully, the questions we give you are sort of simple. There are other sort of more algorithmic ways to arrive at that, but there's not just one algorithm. You sort of still have to inspect the recursive form. Maybe we'll look at that a little bit later. But for this one, we can guess at a solution. Let's guess at f of n equals n squared plus 5. And that seems to fit. F of 1, right, is 1 squared plus 5 is 6. F of 2 is, 2 squared plus 5, which is 9. So that seems to fit. So this is our guess. And now we want to prove that this is true for all f of n. Okay. So yeah, any questions so far? Is everybody, as long as we're clear on what we're doing? Okay, so I have my recursive definition of my function, I have my stopping condition, and I have my closed form, my guess at what the closed form is, and now I want to prove it. So I'm going to prove by induction. So induction and recursion go hand in hand. So most of your proofs of this type, probably nearly all of your proofs will be by induction. So yeah, for induction, I want to prove the base case. I know f of 0 is equal to 5. I want to show that that holds in this case. Well, hopefully that should be kind of obvious. F of 0 is equal to n squared, which is 0 squared, plus 5, which is 5. So our base case holds. So far, so good. Now we want to do our inductive case. So we want to take a value of n that's greater than 0 and assume that our claim is true for all values. Well, in this case, n minus 1. Right? We're using n minus 1 because that is the form that it appears in our recursive function. This is using weak induction. There's such thing as strong induction, but for our purposes, this is sufficient. So we're going to assume it's true for n minus 1. In other words, I take my closed form here, and I assume that this is true. So f of n minus 1 equals n minus 1 squared plus 5. We're going to assume that's true. We know it's true for 0. We're going to assume it's true in general and use that to prove this. All right, so this is what we want to show, and we're going to show it by using the recursive definition and this inductive hypothesis. So our recursive definition is here, so we simply write that down. And then we're going to, by our inductive hypothesis, we're assuming that this is true. So we're going to substitute this in for f of n minus 1 here. Okay. And then after that, it's just algebra. And I want to show that we get to here. Well, I expand out n minus 1 squared, and I get n squared minus 2n plus 1 plus 5 plus 2n minus 1. Okay, so a bunch of stuff is going to cancel here. Minus 2n plus 1 minus 1, and I'm simply left with n squared plus 5, which is what I wanted to show. Okay, so that's, yeah. So that's a very simple version of induction. So for induction, you prove the base case is true. So I'm trying to prove this. I prove that's true for the base case. And then by my inductive hypothesis, I assume that it's true for values smaller than n. And then I use my recursive definition, substitute in my inductive hypothesis, and hopefully get back to here. Okay, so the steps are always the same for induction. You just got to follow them, and even if you don't quite understand always what's going on, the steps are always very clear what you should be doing. So, any questions? All right. Yes. So we've shown it for the base case. We've shown it in the inductive step. So that means for all values n, this is the closed form of this recursion, along with this base case, right? So I do not have a full definition unless I have both of these things. If I have both of these things, then the function becomes well-defined. Otherwise, it can have a variety of values. Okay, so let's look at another simple version, simple function, recursive function. So I have a function g from the integers to the integers. G of 0 is equal to 1. That's my base case. And my recursive definition, g of n is equal to n times g of n minus 1. Again, it's a function defined in terms of itself. Okay, so let's substitute in some values. Well, we know g of 0 is 1. G of 1 is equal to n times g of 0. So 1 times 1 is equal to 1. Sorry. Yeah. G of 2 now is equal to n times g of 1. So that's 2 times g of 1. Right, so 2 times 1 is equal to 2. Hopefully, maybe we're starting to see a pattern here. I can do g of 3, so it's 3 times g of 2. 3 times 2 is 6. Maybe you're not seeing the pattern here, but if we go, we could expand backwards, I suppose. And here, let's maybe go one more. So g of 4 is 4 times g of 3, which is 4 times 6 is 24. Maybe these numbers aren't a clue, but if I expand backwards, I say g of 4 equals 4 times g of 3. Well, if I expand g of 3, it's 3 times g of 2. So that's 4 times 3 times times g of 2. G of 2 is equal to 2 times g of 1. So 4 times 3 times 2 times g of 1. And g of 1 is, of course, 1. 2. Yeah. Yeah. So we're getting kind of a 4 factorial vibe from this. Right. So, and this sort of, if I take any value of g and I expand it out and then walk backwards like this, I should get something similar to this. So we're going to guess a factorial here. All right. Everybody clear on what we did there? Okay. You're going to be doing similar things on your assignments. So our claim, for all n greater than 0, g of n is equal to n factorial. So now we need our base case. Our base case is given to us. All we do is plug in 0. So g of 0 is equal to 1. And our closed form n factorial is 0 factorial. By definition, that's also 1. So our base case is true. Now I have my inductive step. which is I'm going to take a value of n that's greater than or equal to 1 and assume that our guess is true for that value, for n minus 1. Right? So g of n minus 1 equals n minus 1 factorial. That's our inductive hypothesis. That's our assumption. Now we write down the recursive definition. We substitute in our inductive hypothesis here. And then we resolve n minus 1 factorial times n is simply n factorial. Okay, so by induction, our guess here is true because it's true for the base case, and it's true recursively. All right, questions? All right. Okay, so those are sort of easy ones. And then now it starts to get a little more complicated. So the Fibonacci numbers, you've probably heard of them by this point. But the definition is, well, f of 0 is equal to 0, f of 1 is equal to 1, and then for values of n that are at least 2, I have f of n equals f of n minus 1 plus f of n minus 2. All right, so this has some interesting properties. It's actually found many places in nature as well, but so I have my base cases in this case, and I have two of them because I have, I have two f of n, or, the Fibonacci numbers are appearing twice now in my right-hand side. So I have f of n minus 1, f of n minus 2, which means I need two base cases. Given those two base cases in this definition, then I can define the Fibonacci numbers for as far as I want to go. Right? I simply add the two previous. So 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. And so on and so forth. So Fibonacci numbers. All right. So can we solve this? And by solve it, so we're going to give you the closed form. So I want to find a closed form for this. This is not quite as simple as the other ones. So we're going to give it to you instead of having you guess. I'll give you a sort of a high-level view of what's going on here. So here I have x squared equals x plus 1, and I can, so this is a quadratic equation that I could solve. I can solve this using the quadratic equation, right? So this is x squared minus x minus 1 equals 0. And then I can use, well, there's a variety of techniques, but I can do minus b plus or minus, what is it? B squared minus 4ac over 2a. All right, so I plug those values in and I get the, so this has two roots. And by roots, we mean two values for x where this is true. One is a positive and one is a negative. And this is, yeah, so I'm not going to solve this, but we'll just give you the answers. The roots are, and if you're a fan of Greek, you can watch me mangle these. But this is phi, I'll call it. I think it's phi. And this is psi. And I will guarantee you I confuse them at some point, but yeah. So phi and psi, phi is 1 plus root 5 over 2. Psi is 1 minus root 5 over 2. These are the solutions to this equation. That means if I plug these values in for x, this will be true. Okay? So we're going to use that, and the reason why we use that, this is a high-level sort of proof. If I take x squared equals x plus 1, this is, well, I can write that as x to the 1 plus x to the 0, right? X raised to the 0 is 1. And then I can multiply by, let's say, n minus 2. So then I get x raised to the n. So I multiply the left-hand side by x to the n minus 2 and the right-hand side times x to the n minus 2, and I get this. And now this is sort of a closed form that matches our Fibonacci. So whatever our closed form is, it should be of the variety that the closed form for f of n is equal to the closed form for f of n minus 1 plus the closed form for f of n minus 2, and this fits that bill. All right, so that's why we use this to get these roots, and then we're going to, these roots appear in the solution to the closed form of the Fibonacci sequence. Now, there's more steps to it than that, but that's sort of at a very high level. We're just taking an equation that we can make look like the Fibonacci sequence. All right, so, and you can, this works for a variety of other Fibonacci-like recursive functions. And you'll see one of those on your assignment. Okay, so we have our two roots. Anybody completely lost? Or everybody okay? Good. Okay, so now we want to show that, so our claim is that given these roots, so we have the roots, but what we don't know is the coefficients, and the coefficients we get from these two base cases, right? So that's, again, I'm going to spare you the details, but our claim is that f of n in the closed form is equal to phi raised to the n minus psi raised to the n over root 5. We're just going to, this looks a lot uglier than what we were doing before, but we're going to do the exact same thing. We're going to prove this by induction. Okay, so we're going to prove the base cases, and then we're going to formulate our inductive hypothesis. We're going to write out the recursive form. We're going to substitute the inductive hypothesis in. All the exact same steps. It's just going to look a lot uglier than the other one. Okay, so this is our closed form. Let's prove this using induction. Incidentally, this is what's known as the golden ratio, right? So this appears all the time in nature. So it's, if you look at the spiral of a snail shell, right? So the ratio of each successive spiral is, you know, equal to the 2 before it or something like that. It's also, roughly speaking, you know, if I look at half of my arm is this part, and they're about the same length, but then this is about the same length as these, and then this is about the same length as my fingers, and so yeah, that's sort of where the golden ratio comes from. It's sort of a natural ratio. It's not, I mean, it's not always precisely this, but it occurs in nature. This sort of rough idea of this ratio. Anyway, okay, so I have my base cases, I have my recursive definition, and I have my guess at a closed form. Again, we're just going to go through all the same steps. I want to make sure we end in time to do some, to take up some test questions. So again, here's what we do know. This is not the induction, but we know that x squared equals x plus 1 has these two solutions. And what that means is that phi squared equals phi plus 1, and psi squared equals psi plus 1. So we're going to use those. And our proof by induction, so we take our base case f of 0. So n is equal to 0. So this is phi to the 0 minus psi to the 0. Anything raised to the 0 is 1. So I get 1 minus 1 over root 5, which is 0. So for f of 0, our base case holds. F of 1 gets a little more complicated. So I have phi to the 1, psi to the 1. So now I have to substitute these values in. These are over 2, so I get the 2 in the denominator here. All right, and then I have 1 plus 5 minus 1 minus 5. I can expand those out. The 1's cancel out. I get root 5 plus root 5 over 2 root 5, what's equal to 1. So the other base case holds, not surprisingly, since we know this is the answer. But yeah, questions so far? Again, this looks really ugly and complicated. It's not as bad as you think, right? If you work through it by hand, it can be hard to follow. It's hard on the eyes, right? There's lots of stuff going on, but working through it is not quite as hard. Okay, so our inductive step for n at least 2, we're going to assume that this is true. So this is our inductive hypothesis. But since we have 2 base cases, we're also going to assume that this is true. Okay. All right. So I write out the recursion, and then I substitute these 2 closed forms, this inductive hypothesis, and I have this. Okay, so I have a common denominator, so I'm going to write it out with the common denominator. And then what I'm going to do is, well, I have a phi here and a phi here and a psi here and a psi here. The psi's are both negative. The phi's are both positive. I'm just going to gather like terms. Okay, so I have now my psi's over here and my phi's over there. I told you I'd mess it up. And psi's over there. Simple enough. Now I have like terms together. I can take out a common factor. The common factor in this is phi raised to the n minus 2. So if I take that out, I get phi raised to the n minus 2. Well, it's 1, right? So phi raised to the n minus 2 divided by phi raised to the n minus 2 is 1. Phi raised to the n minus 1 divided by phi raised to the n minus 2 is just phi. So I have phi raised to the n minus 2 times phi plus 1. And I do the same thing for my psi's, right? So the exact same process. I'm taking out the common factor of psi to the n minus 2, negative psi to the n minus 2. Okay. At this point, we have phi plus 1 and psi plus 1. And we have, well, we know because these are the roots to this equation that phi plus 1 equals phi squared, psi plus 1 equals psi squared. So I can substitute those back in. Psi squared, phi squared. Of course, phi to the n minus 2 times phi squared is phi to the n, and psi to the n minus 2 times psi squared is psi to the n. Right, and that is exactly what we wanted to show here. So that is our closed form. We've proven it. This is our closed form for the Fibonacci sequence. All right. Questions on that? Okay. Yes, so yeah. It's exactly what we did before. It just looks a lot uglier, I guess. Okay, so now that we know the closed form, let's see what sort of problems that we can solve using the Fibonacci sequence. So we want to count certain things recursively, and that can help us out. So we're going to look at bit strings, but we're going to look at special bit strings. We're going to look at bit strings that do not have 2 zeros in a row, right? So, 1, 0, 1, 0, 1, 1, 1, 1, 0, that's a 0, 0 free bit string. I have zeros in it, but I don't have 2 zeros in a row. If I had something like this, well, that's not a 0, 0 free bit string because I have 0, 0 in it. So I know how to count normal bit strings. I want to count the number of bit strings that do not have 0, 0 in them. And I'm going to say that Bn is equal to the number of 0, 0 free bit strings of length n. Okay, so first thing I want to do is I want to look at some small values of n, right? So if I have a bit string of length 1, well, I have 0 and I have 1. Those are both bit strings of length 1, and they're both 0, 0 free. So in this case, I have b of 1 is equal to 2. So I'm just establishing my base cases. Okay. So now I look at b of 2, n equal to 2. Well, I have 0, 1. I also have 1, 0, and I have 1, 1. I could also have 0, 0, but of course that has a 0, 0 in it. So that's a bit string of length 2, but I'm going to not use that one. So out of the 4 available, these are the only 3 that match that criteria. So for bit strings of length 2, my b of n is equal to, my b of 2 is equal to 3. All right, so I have 2 base cases. We'll do one more just for fun. N equal to 3. I can't have 0, 0, 0 or 0, 0, 1, but I can have 0, 1, 0. I can have 0, 1, 1. I can have 1, 0, 1. I can have 1, 1, 0 and 1, 1, 1. All right, so in this case, my b of 3 is equal to 5. Yep. I only need 2, but we're doing 3 just to. It depends on the recursion. So in this case, because I know that we have we're going to have two sort of recurrences on the right-hand side. So in general, so the Fibonacci sequence is f of n minus 1 plus f of n minus 2. So I know I need two of these, and I know they're in sequence, right? So I need f0, f1 plus this. Basically, if given my base cases and this recursive definition, can I figure out every number? That's sort of the heuristic, I guess. But in general, yeah, I have two terms here, so I need two base cases. Other questions? Okay. All right. So I derived three base cases just for fun. Now we want to find a recurrence for this number b of n. So what I'm going to do is I'm going to take all of the bit strings of length n, and I'm going to say this big orange thing is my set of these bit strings. These are all of the 0, free bit strings of length n. And now I'm going to divide them into two subsets. The first subset is the set of all bit strings of length n that are 0, free and that start with 1. And the second subset is all of the bit strings of length n that are 0, free and start with 0. Okay, so altogether, these are all b of n of these bit strings with length n, and yeah, they're all 0, free. Okay. So now what I want to do is I want to count these subsets. So up here, I have all the 0, free bit strings of length n that start with 1. So how many of them do I have? Well, I'm going to define this recursively. So I know what the first bit is. So after that bit, I have n minus 1 bits, and I know that these are all 0, free, right? So that means if I wanted to count all of them in here, well, that's equal to all of the bit strings of length n minus 1 that are 0, free, right? Because once I write a 1, I can write a 0 or a 1 after it. It doesn't matter, as long as the rest of the bit string is 0, free. Okay, so yeah, this is, if I count all of the ones that start with 1, it's equal to b n minus 1. Make sense? Questions? Okay. All right, so I have the start of my recurrence here. Now I want to count all the ones that start with 0. So let's look at that. So if I start it with 0, then what can my next bit be? Yeah, it has to be a 1, right? It can't be a 0. If I write a 0, then it's not 0, free. So if I write a 0, that means my next bit has to be a 1. So now this is, if I look at the rest of this, as long as that's a 0, free bit string, I can put anything I like there. So these have all of length n minus 2, because they're length n, but I know that the first two bits are fixed. So then if I count everything in this subset, it's equal to the number of 0, free bit strings of length n minus 2. Okay, so now I have all of my bit strings of length n that are 0, free, and that is equal to all of them of length n minus 1 plus all of them of length n minus 2. Right, so I have my recurrence now. B of n is equal to b of n minus 1 plus b of n minus 2. All right, so I have my recurrence. I have my base cases. I have more than I need in this case, but that's fine. So now I have enough to sort of express this recurrence. Okay. So let's write out. So here I'm going to have a little table. I'm going to write my Fibonacci sequence, because what I noticed is that this recurrence and this recurrence are the same. The base cases are a little bit different, but we'll see in a second. So if I write all of the Fibonacci numbers from 0 to 7, I get 0, 1, 1, 2, 3, 5, 8, 13, and then I'm going to match these up with my b of n. So I have b of 1 is equal to 2, so I could put that here. My b of 2 is equal to 3, so that matches here. B of 3 is equal to 5, that matches here. but B of 1 and B of 2 are enough, right? Because I know that B3 equals B2 plus B1, and F5 equals F4 plus F3. So that's going to be the same here. And I know that F6 equals F5 plus F4. Well, B4 is equal to B3 plus B2. So this is the exact same sequence. It's just, off by a little bit. I skipped the first two numbers. All right, so I can express this. I can say B of n is equal to the n plus second Fibonacci number. And I already know a closed form for that, so I'm good. Okay, so if you can match it up to the Fibonacci sequence, then that's sufficient to, to be able to count the number of these things. All right, questions? All right. 46. Okay, so let's look at another thing we can count using recursion in the Fibonacci sequence. I'm going to take a number n, an integer, and I'm going to write it as a sum of 1s and 2s. So what does that mean? Well, I can say 5 is equal to 1 plus 2 plus 1 plus 1. So I can only include 1s and 2s in my sum, but I can arrange them any way I want, right? I can say this, or I could also write it 2 plus 2 plus 1, or I could write it 1 plus 2 plus 2. So there's all these ways to write 5 as a sum of 1s and 2s, right? So the order of the 1s and 2s matter, but I can, these are considered interchangeable. Okay, so how many ways can I write these sums? Well, we're going to start with our base cases. So we're going to take low values, we're going to count them explicitly, then we're going to try and derive a recurrence. And if we're lucky, we'll map it to the Fibonacci sequence. And if we're not, then we have to guess and check using induction. But all right, so if I express 1 as a sum of 1s and 2s, well, 1's just equal to 1. So I have one term in that. Or one way to count 1 as a sum of 1s and 2s. 2 I can count as 1 plus 2, or I can count as 2. So there's two ways to do that. So my S of 2 is equal to 2. 3 I can have 1 plus 1 plus 1, or I can have 1 plus 2, or I can have 2 plus 1, and that's it. So S of 3 is equal to 3. 4, just for fun, 1 plus 1 plus 1 plus 1, or 1 plus 1 plus 2. And then I can place this 2 in 3 different places. Or I can write it as 2 plus 2. So my S of 4 is equal to 5. Okay, so I have enough base cases here, hopefully. So let's try and figure out how to write this recursively. So again, I'm just going to do the same thing I did with the bit strings, essentially. I'm going to look at the ways that I can start this. Let's say I had n greater than or equal to 5. If I start with a 1, I can start with a 1 or I can start with a 2. Those are basically the only two choices. If I start with a 1, all of this has to sum to n. That means whatever this expression is here has to sum to n minus 1. And if I start with 2, since this has to sum up to n, whatever summation I have here has to sum up to n minus 2. So now how many ways can I express n as a sum of 1s and 2s? Well, it's going to be S of n minus 1 plus S of n minus 2. Does this make sense? Questions on that? Okay. All right, so yeah, S of n minus 1, S of n minus 2. Again, now I have this same recursive recurrence that looks a lot like the Fibonacci sequence. So we're going to guess that maybe we're looking at the Fibonacci sequence. I look at my base cases, 1, 2, 3, 5. 1 can be here or here, but I know S2 is 2. So if I do something like this, right? That's starting to make a lot of sense. And now because this recurrence is the same and I sort of have the same base cases, I can just keep going, right? All right, so it looks like my sequence here is equal to, S of n equals f of n plus 1. And I know the closed form, so if I wanted to count these, I could for any value n. All right, questions? Okay. Yeah, how much time do I have here? All right, I think we can quickly go through this and we'll still have time to do the, so this is a non-recursive definition for these Fibonacci numbers. So I can come up with an alternate expression for these 0, free bit strings just by using what we've learned already in chapter 1. So again, B of n is the set of 0, free bit strings of length. Well, yeah, that would be B of 9, I suppose. So 0, free bit strings of length 9, but now I want to count 0, free bit strings of length 9 that have exactly 3 ones in them. Right, so yeah. I'm going to task 1, I'm going to write the 3 ones in a row. There is one way to do this. Task 2, I'm going to place 6 zeros between the ones such that no 2 zeros are next to each other. So I'm going to write down 3 ones, and I'm going to place 6 zeros. I have now essentially 1, 2, 3, 4 locations for my 6 zeros. So is it possible to have a 0, free bit string of length, of length 9 with 3 ones? Right. And that's because of the pigeonhole principle, right? We have 4 buckets and we have 6 pigeons. So that means we're going to have a bucket with at least 2 pigeons somewhere. Okay, so the number of these is 0. Even using the product rule, since I'm multiplying these together, if one of these comes up 0, the whole thing is 0. So there's no bit strings of length 9 with 3 ones. What about 4 ones? 2. Actually, I think we can do this. Write down 4 ones, place the 5 zeros between them. Okay, so here's our task. We wrote down 4 ones, and now we have 1, 2, 3, 4, 5 buckets, and we're going to place 5 zeros between the ones. So how many ways can we do that? Well, we have 5 places. We're going to choose 5 of them, right? So there's only one way to do that. Right, so then this is 5 choose 5 ways, or 5 choose 5 strings of, in this case, length 9 with exactly 4 ones. What if I said 5 ones? Well, now I have 1, 2, 3, 4, 5, 6 spaces, and I have 4 zeros to place between them. So how many of these strings do I have? Yeah, so I'm going to choose 4 of these. So maybe here, 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 and here. Right, and then it's a bit string. My bit string is 1, 0, 1, 1, 0, 1, 0, 1, 0, and it's 0, 0, free. Right, so this was 6, choose 4. Yeah. All right, so if I write down 6 ones, now I have 7 spaces, and I have 3 zeros to place between them. So I have 7 choose 3 of these strings where I have, they're 0, 0, free, they're length 9, they have exactly 6 ones. So I can formulate the Fibonacci number slightly differently. So in this case, this is B9, which I know maps to F11, and I can express it like this. I can just look at all the sum. So I just noticed the pattern. I expressed it out. I'm not going to prove this. I think the proof is sort of obvious. But I can express it like this, where these all are 0, right? And then starting from here up to 10 choose 0, if I sum those up, I actually get the 11th Fibonacci number. All right, so using our rules of counting, we can come up with an alternate form for this, and perhaps even, I don't know, I would have to look a little more closely if we can get a different closed form or a closed form, but yeah. So this is, I mean, yeah, we have an alternate way to express the Fibonacci sequence like this. So there is a closed form for this kind of summation, and that is, I mean, the whole point is to show you that, again, there's many ways to count something, right? So there's not just one way. It's almost never just one way. There's many, many ways to count them. But that's sort of a non-recursive, iterative way. Any questions? All right. Okay. So that's heavy stuff, but let's look at some. So I'm going to look at least one midterm. I have 2 set up, and we'll just go through. I think it's only the first 9 questions that pertain to this test, and we'll just solve them and look at some of the trickier ones, and see how they're solved. All right, I think I wrote my answers down here. And this is the, if you want to look it up, it is the winter 2018 midterm. Okay, so again, one of the most important things when you're approaching these questions, you have to figure out what it's asking, right? Sometimes that's not quite clear. There's a lot of sets and things like that, and you're probably not used to thinking in these terms yet. So in question 1, 2, and 3, we're going to consider strings consisting of 12 characters. So you know this, but now our alphabet is limited to these 5 characters. Okay, so that should be simple enough. We're going to say that the positions are labeled 1 to 12. So now we're going to count specific subsets of these strings. So all of the strings together you should know as, so I have 5 choices for each spot, and 12 spots, right? So if I count all of the strings of length 12 using these 5 characters, I get 5 to the power 12. So that's probably going to be my universe if I need it for a complement rule or something like that. So now I'm going to look at how many of these strings have the property that each even position contains one of A, B, or C, and each odd position contains one of D and E. Okay, so my strings are length 12. That means I have 6 positions that are even and 6 that are odd. And so, and I know exactly where they go. So I know my odd positions. There's really only one way to choose it, but each of my 6 odd positions, I have to choose one of these characters to put there. Right, so I have 3 choices for my odd, and I have 6 odd positions. And, or sorry, 3 choices for my even, and I have 6 even positions. And then I have 2 choices for my odd, and I have 6 odd positions. So this is what I should have. Of course, this is, sometimes we're a little tricky here. So which of these answers corresponds to this? Yeah, actually A does. So if because multiplication is commutative, I can write all these out and then mix them around. So the way I have it written here is this times 2 times 2. So I'm just going to write it as 3 times 2 times 3 times 2, 6 times, so that's 6 to the 6th, right? So there is sort of these little translations that happen that you should be aware of. Okay, does that make sense? Questions on that? Okay, so it's actually A. Let me verify that I didn't. Yeah, so it's A. Okay. How many of these strings, same strings now, have the property that each even position contains A, B, or C, or each odd position contains D and E? So when you see or, now these are you're probably going to use either the sum rule or inclusion exclusion. Okay, so each even position contains one of these, and the odd positions can be whatever, right? So that's this set here. So I have 6 even positions, and I have 3 choices for each of them, so 3 to the 6. I have 6 positions left over that can be A, B, C, D, or E. Right, so that is 5 to the 6. This one I have the same thing. I have 6 odd positions, but I have 2 choices now. And then for the remaining even positions, I choose anything, right? So that's all of these strings we're counting here. Now this or means that I can just add them together, right? That's the sum rule, but are there strings where both of these things are true? Well, yes, there is. Actually, we answered that up here. So it's 3 to the 6 plus 3 to the 6 times 5 to the 6 plus 2 to the 6 times 5 to the 6 minus 3 to the 6 times 2 to the 6. So what do we got here? Is it this one? 2 to the 6, 5 to the 6, 2 to the 6, 3 to the 6. Yeah, so it looks like C here. All right, let's make sure. Yeah. Right, makes sense. I'm going through them quickly as you would sort of be expected to do on the midterm. Okay. How many strings contain at least 2 A's? All right, so at least 2 A's. And I mean, I look here and I see there's some minus signs, so I'm probably going to use the complement rule. I know 5 to the 12 is the universe. So right away, I can eliminate C and eliminate D. So I have a choice between A and B. So 5 to the 12 minus no A's minus 1A. Right? So the complement of at least 2 A's is that I have exactly 1 A or exactly 0 A's. So 0 A's is easy enough. How many strings do we have with no A's in them? 4 to the 12, right? I have 4 choices for each of my 12 locations. For 1A, all right, so how do I do this? Sequence of tasks, right? First thing, choose a location for my A, right? So I have 12 possibilities, and look, well, it's even given us a hint. So 12, and now I have to choose the rest of my string. So I've placed my A, now I have 11 locations left, and I have to place one of the 4 remaining characters. They can't be A's. I have exactly 1 A, so I have 4 to the 11. So it's looking like A is the answer here. And yes. Okay, good questions? Yeah. Okay, so all right. All right, beer and cider. Okay, so again, we have to figure out what exactly is being asked here. So Eliza's neighborhood pub serves B different types of beer and C different types of cider. So now we have Eliza and 6 friends. She orders 1 drink for everyone, so 7 drinks altogether. So she orders a beer or a cider for each friend and 1 cider for herself. Different people can get the same type of beer or cider. We're allowed repetition. So how many ways can Eliza place these orders such that exactly 4 people get a beer? And we have a hint here. So we know Eliza gets a cider, right? So, so of her 6 friends, we have to figure out which 4 of them get a beer. So how many ways are there to do that? So I have 6 friends. I have 4 of them I'm going to choose. It's just 6 choose 4. So I can eliminate this. So 6 choose 4, and now I have, so those 4 people, I have B choices for their, the types of beer that they're going to get. So 6 to the 4, yeah, 6 choose 4 times B to the 4. Now, how many ciders do I have to choose? 2 or 3? she has two friends that get ciders, but she also has a cider. Eh? It's a little bit tricky. Yeah, so she knew she was getting a cider, she just didn't know what kind. So I do need to actually count how many ways she can get a cider. So yeah, B to the 4, C to the 3. So that should be B. And we're good. So far, so good. All right. Questions? Yep.
Just to clarify, the binomial is 64 because we know she gets a cider. So now we're determining who gets the 4 beer, right?
Exactly.
For the types of beers that we're looking for, right? That's what the type of beer is, and then C to the 3 is just same thing, keep the cider. And then we include it because we know she has a cider, but it's not really cider.
Right. Yes, it is. It is almost exactly what I asked on the assignment, but with the little twist that we know she's getting a cider, right? So it's instead of 7 friends on the assignment, it was just a round of 10 drinks, but it is Newton's binomial theorem. Okay, so you might see a question like this. This is set theory. A group of 100 people, 60 do not like Donald Trump. It's a little dated, but and do not like Kim Jong-un, and 25 like Kim Jong-un. Okay, so there's 100 people. You can assume that everybody it's binary, right? So they either like Donald Trump or they don't. And they also either like Kim or they don't, right? So if it's not one, then it must be the other, right? So that's when you're counting, you can assume that. So how many people in this group like Donald Trump and do not like Kim Jong? So let's say K equals like Kim, T equals like Trump. All right, so what do we know and what do we want to find out? So we know that 25 like Kim Jong-un, so we know that 75 do not like him, right? Because everybody has to either like him or not, and there's 100 people. Okay, so K is equal to the universe minus, we can call that K naught is equal to the universe minus K equals 100 minus 25. 75 people do not like Kim Jong-un. And I want to find out how many do not like, I want to find out how many like Donald Trump and do not like Kim Jong-un. So what I'm going to use is this, and I forget the name for it. But if I want to find the size of this set, for instance, I can take, and I have my set broken down into, sort of pro-Donald and anti-Donald. If I take a set K naught, some will be in some set and some will be in the other. But if I take the intersection of K naught with likes Trump and doesn't like Trump, then I can count the entire thing. So what I mean by that is I can write this as assuming that these are all the values. This intersection union with this intersection. Okay, so this is just 1805 set operations, but you might be asked something like this. So what do I know? I know this value, and I also know this value. So this is 60. So 75, and what I'm trying to find is this one. Using the sum rule, this is what? 60, yeah. Oh, thank you. Okay, so then I just solve for my number, I get 15. So that's, using these set operations in the sum rule. And so this is not stuff we covered a lot explicitly. We covered it a bit with inclusion, exclusion, but it's sort of stuff you should know from 1805. There are easier ones than this that are similar to the one that appeared on the assignment, right? So you also had an assignment question. Yep. Sure. Yeah, but I mean, yes. you could expect, if you saw any of these questions, you should not be surprised, right? So yeah, this is, I mean, I literally, I modeled this course off of how McKeel teaches it. So you should expect very, very similar things. Okay, how are we doing? In the city of short last name, I want to make sure I got that right. So it's 15, right? So that should be B. Yeah, so 15B. Okay, short last name. Every person has a last name consisting of one uppercase followed by two lowercase. No three letters in a last name can be equal. That's actually, that looks like it's phrased wrong, right? Yeah, so it should be no two letters in a last name can be equal. Right, so Zax is not a valid, so XAX is not valid while Lin is valid. Okay, so you hardly ever find mistakes in McKeel's midterm, so this is, I don't know, this is sort of a remarkable thing. All right, so I can't repeat any letters, which means the fact that one is uppercase and two are lowercase doesn't even matter. I have 26 to choose from for each of them. But what is the minimum size of the population of short last? Oh, this is a pigeonhole principle, but it's got a little bit of counting in it, right? So how many of these last names do we have if we can't repeat any letters? Right, 26 times 25 times 24, right? It's just the product rule. The first letter, I have 26 choices. The next letter I can't repeat. So I have 25. And the last letter, I can't repeat either of the first two, so I have 24. Right. And then if it was pigeonhole principle, I would just add one to that to say that, well, somebody's definitely going to have the same last name if I have this many people. But all right, so that's a bit of counting. Questions on that? Yeah. Well, I mean, it's multiple choice, right? So the answers are there. So yeah, so you should be able to convert back and forth in the worst case, right? So 26 times 25 times 24 is equal to 26 factorial over 23 factorial. Did I get that right? I got it wrong on the assignment day. But yeah, I got it right here. All right. Okay. So here, one of the more tricky ones. And how much time we got left? Okay, we got enough time for both. Let n greater than or equal to 2 be an even integer. So what does this count? Oh my goodness. Okay, so what we're going to do is we're going to expand it out and we're going to just look at some of the values that we get. So if I have k equal to 0, I have n choose 1. If I have k equal to 1, I have n choose 3. I have k equal to 2, I have n choose 5. So where does it end? With k equal to n minus 2 over 2. So 2k plus 1. So let's take a look. So k equal to n minus 2 over 2. And I want the value of 2k plus 1. So that's equal to 2 times n minus 2 over 2, which is n minus 2 plus 1. Right? Makes sense. I skipped a step, but does everybody follow? Okay. So this is equal to n minus 1. Okay, so the highest value for k gives me, this is plus dot 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 plus n choose n minus 1. Okay, so what's the pattern we notice there? These are all odd numbers, right? So all the odd numbers from 0 to n. So what would fit with that? The number of bit strings of length n. Well, I know the number of bit strings of length n is, I would just have k equals 0 to n. The number of bit strings of length n minus 2 divided by 2, well, maybe, but not likely. Actually, that would be, you would have to count it differently. So we'll put that on the back burner. Number of bit strings of length n having an odd number of zeros. right? So would that track? So I want to count all the bit strings of length n that have 1 0. That's there. All the bit strings of length n that have 3 zeros. That's there. 5 zeros is there. So that sort of seems to be what we're looking for. Length n with the number of zeros plus the number of ones is at most. Yeah, that doesn't seem to make sense. So it seems like C is the one that would be our best guess. In fact, C is true. C is definitely true. It's just a question of whether the other ones are true. But if you know C is true, then you don't have to, you don't care. Yeah, so C is true. Okay. Now 8. So 8 is again, the hardest part is probably the hardest part is figuring out what's being asked here. So I have a number m, at least 34, and an n, and I have a set A and a set B. A and B together have m plus n elements, I can see. All right, so I'm going to count the number of subsets X, right, of the union. So this is a subset of A union B. So I know there's m plus n elements. Now X has a size K, where K is at least 17, and at most n plus 17. And, jeez, X intersect A is 17. So what does that mean? I've chosen K elements, and X intersect A is 17. Yeah. Sorry, the what? Well, it might be, well, that's, so what I'm saying is that there's 17 elements here, right? So X, so what does that mean? I had to choose some elements from A. How many did I choose? I chose 17. For this subset X, 17 of those elements come from A. I mean, this is nasty. Yeah, I don't think you, well, this might be probably as harder than anything you see, but hard questions are still going to appear. So what does this mean? It means for my subset X, I choose 17 of them from A and the rest from B. So K minus 17 from B. Possibly, I don't know yet. Okay, and all the elements of X intersect A are even. So I have, good grief, 17 even elements in X. So 17 elements, even elements are chosen from A. And then, what is it? K minus 17 are chosen from B. So once you decipher everything, that's what you're looking for. Okay, so 17 even elements. So my A, M is an even integer. I have M elements, so I have M over 2 to choose from. You know, and we got a hint here. I'm choosing exactly 17, so the first part of this expression is M over 2, choose 17. And now I have to choose K minus 17 from the N elements in B. So it's looking like this one. Right? And in fact, you can probably, I mean, just by the first term alone, you can really rule out all of that. So it should be A. Yeah. So yeah, once you know this part, of course, even if you don't know the rest of the answer, you have a pretty good guess that it's going to be A. Yeah. So we're choosing 17 elements from M, but only even ones. Yeah. So we have half of them to choose from. And that is, the way that is expressed is something else. But all right, questions, other questions? Yeah. That's this part here. So the intersection of the set X and the set A is exactly 17. So X consists of K elements from A and B. And this means that it has 17 in common with A. So it's, yeah. Other questions? All right, this should be easy. What's the answer to this? Number of linear equations. Sums to 33, I have 4. So how I like to do it is I have, so you can do the formulas, of course, n plus k minus 1, choose k minus 1. I like to just count these plus signs. So I get 33 plus 3 is 6, choose 3. So that would be B. If I use this, the k is equal to 4, and I get the same thing. Right? I like counting plus signs. That's just whatever. This minus 1, plus 1 stuff, there's so many different versions that it's easy to mix up. Okay, good. I think that's it for this one. Yeah, questions? Yeah. Yeah, essentially. So these are, I mean, you're going to see other stuff as well. So remember, permutations of a finite set. So if I have a set of, say, 10 unique things and I line them up, there's 10 factorial ways to permute them. If I have a set of 20, if I have a set of 10 unique beer bottles and 10 unique cider bottles, and I give you some constraints, there's still 10 factorial ways that I can arrange each of those. Yeah. Sorry? I'm going to, it might be the same one. Actually, you know what? I'll try and do, I just want to do 5 basically, and then I'll do the other one. So then, yeah, you guys can see some different questions. But I think everybody should see 5 because it's a little outside of what we do. Yeah. Pascal's triangle is to help you. It's more of a thing that sort of encompasses all those identities. It does show up in certain questions, summation questions, that I did show you where you step right up and then left. So those are on the either the old midterms or the old finals. Maybe, I don't know. But yeah. All right. Other questions? Okay. All right. Yeah, I'll see you guys next class. Good luck. Bring pencils and calculators. And,